Hello and welcome to Electromagnetics 1. This is lecture number 19. Today we're going to be talking about three big topics. The first is the equation of continuity, the second is displacement current, and the third is the time-harmonic Maxwell's equations. Well, in order to understand displacement current, we first need to talk a little bit about the equation of continuity. The principle of conservation of charge dictates that the rate at which charge decreases in a given volume must be equal to the net outward current flowing through a surface bounding that volume. The current I out flowing through the closed surface is given by the following. I out is equal to the flux of the electric current density J through the surface. And that flux of J is equal to the negative time derivative of the total charge enclosed by that surface. It makes a certain amount of sense if you think about it from this perspective. Obviously, a current is just simply moving charge, and so if current is leaving a particular volume through passing through a particular surface bounding that volume, if current is leaving, then the total charge inside that surface has to be decreasing. So that's where the minus sign comes from there. Well, we can apply the divergence theorem to this term right here, the flux of J, and the divergence theorem simply says that the integral of J dot ds integrated over a particular surface is equal to the divergence of J integrated throughout the volume bounded by that surface. Okay. All right. Well, what else can we do that may help us understand this a little bit better? One observation that we can make is that the total charge Q enclosed is equal to the integral of the volume charge density rho sub v throughout that particular volume. Okay, so in this expression right here for Q enclosed, I can substitute in the integral of the volume charge density rho sub v throughout that particular volume, and that's all that I've done here with this first equation. Okay, so the minus time derivative of the total charge enclosed is equal to the minus time derivative of the integral of the charge density throughout the volume. Okay, and then from here to here, I'm just simply bringing this time derivative in to act on the charge density term. Okay. Now we can make a couple of substitutions. We can substitute this expression from 2 and this expression from 3 into this equation, and equation 4 results. Equation 4 says that the integral throughout the volume of the divergence of J is equal to minus the integral throughout the volume of the time rate of change of the charge density, the volume charge density. Okay. It turns out that this law also holds pointwise and as well as in aggregate, so we can drop these integrals and arrive at this expression right here, which is that the divergence of the electric current density J is equal to minus the time rate of change of the volume charge density rho sub v. This expression right here, equation number 5, is the so-called equation of continuity. It is derived straightforwardly from the principle of charge conservation, which is essentially the principle of conservation of mass. It's essentially a conservation law, but it's a little differential equation, and this differential equation must hold anywhere in space where we're talking about macroscopic quantities. Okay. Well, the equation of continuity is related to our next topic, which is the displacement current. Ampere's law for magnetostatics is given by the following. The curl of the magnetic field is equal to the electric current density J. One thing we can do is we can take the divergence of both sides of this equation, all right, and take advantage of the fact that the divergence of the curl of any vector is in fact equal to 0. So divergence of the curl of H is equal to 0, just by virtue of the fact that the divergence of the curl of any vector field is always equal to 0, which also implies then that the divergence of the electric current density J is also equal to 0. However, we just showed that the equation of continuity requires that the divergence of the electric current density J is equal to minus the time rate of change of the charge density rho sub v, which is not necessarily equal to 0. So we have a conflict here between the magnetostatic Ampere's law and the equation of continuity. And so somehow this conflict needs to be resolved. In order to resolve the contradiction between the equation of continuity and the magnetostatic Ampere's law, we're going to add a term to the right-hand side of Ampere's law. So we're going to modify Ampere's law to be the curl of the magnetic field is equal to the impressed current J, just like before, the impressed current density J, and another current density, J sub d. All right, and we'll see if we can figure out what the expression for J sub d is. In other words, how is J sub d related to the fields, the electric field and the magnetic field potentially? That's what we need to find out. Okay. Well, we're going to play a similar game here. We're going to take the divergence of both sides of equation 9 again. So taking the divergence of both sides, and again taking advantage of the fact that the divergence of the curl of any vector field is equal to 0, implies that the sum of the divergence of J and JD has to be equal to 0. Okay? Which implies that the divergence of the impressed current density has to be equal to the negative of the divergence of J sub d. Okay, well, we know from the equation of continuity that the divergence of J has to be equal to the negative time rate of change of the charge density rho sub v. Okay, so divergence of J has to be equal to this quantity, which is equal to the negative divergence of J sub d. Okay, now Gauss's law, the point form of Gauss's law, says that the divergence of the electric flux density D is equal to rho sub v. So for rho sub v right here, we may substitute in the divergence of the electric flux density D. And this is the only quantity that depends on time, so this time derivative just acts right here on the electric flux density D. So look, now we've got a relationship here between J sub d and the electric flux density D. In fact, we can drop the divergence here because we're taking the divergence of both quantities, and it turns out that J sub d is in fact simply equal to the time rate of change of the electric flux density D. So the displacement current, J sub d, is defined to be the partial derivative with respect to time of the electric flux density D. So this is, in fact, right here, this term is the term that we need to add to the right-hand side of Ampere's law. So let's go ahead and do that. The curl of H, curl of the magnetic field, is equal to the impressed electric current density J. This term is typically due to sources, plus the partial derivative with respect to time of the electric flux density D, the so-called displacement current. And this is, in fact, the dynamic form of Ampere's law. So we've got one more of our final Maxwell's equations now. Now let's try one more thing before leaving this. Somehow this equation has to contain or imply the equation of continuity, because the equation of continuity has to hold, we said, pretty much all the time. So let's again take the divergence of both sides of the equation here. The divergence of the curl of H is 0, which implies the divergence of J plus the divergence of the displacement current. That sum has to be equal to 0. So therefore, the divergence of J is equal to minus the divergence of this displacement current. And again, we know that the divergence of D is rho v. You can make that substitution in. Voila, del dot J is equal to minus the partial of rho v with respect to time, which is our equation of continuity. So Ampere's law, in its most general form here, implies the equation of continuity. It's completely compatible with it. Well, now that we have all of our dynamic Maxwell's equations, we can write them all down. The first one here is the dynamic form of Faraday's law. The second, the dynamic form of Ampere's law. The third, Gauss's law. And the fourth, Gauss's law for magnetic fields. It's worth pausing here for just a moment to note that, again, these four equations are extremely general. They are so general that they govern electromagnetic phenomena from scales starting around tens of nanometers all the way up to intergalactic scales. So they cover a simply enormous range of scales and therefore are applicable to a simply enormous number of situations. These equations are incredibly powerful, but they're also extremely general. And so oftentimes it is useful to try to simplify them for some special cases of note. One of those special cases is that of sinusoidal time variation. So if it is known a priori that the fields vary sinusoidally, we can simplify the four Maxwell's equations somewhat. What I'm about to do now is very similar in spirit to AC phasor analysis from circuit theory. So I would recommend that you go back and get your circuits book out and have a look at the phasor analysis section in there, because we're going to be doing the exact same thing. We're going to pass from time domain to frequency domain. We will solve a problem in frequency domain and then go back to time domain, essentially by taking an inverse phasor transform. Okay. Well, equation 16 says that all time harmonic fields may be written in the following way. The time domain field is equal to the real part of the phasor, E sub s, as a function of r. Our notation for phasors will be, we will include a subscript of s to indicate a phasor. So E sub s of r here is a time-independent, complex-valued phasor. Okay? And in order to get back to time domain, you multiply the phasor by e to the j omega t, where omega is the frequency in radians per second, and you take the real part of that quantity to go back to time domain. All right? Now, let's talk a little bit about phasors. Remember that phasors are complex numbers that have both a magnitude and an angle. Okay, so this phasor here, E sub s, has a real part A and an imaginary part B. It can also be written as the magnitude of the phasor, E sub s, times e to the j theta, where theta is the angle. Okay, let's look up here at figure 1 by way of review. Phasors can always be depicted on a two-dimensional plane, where so this blue arrow is the phasor. the length of the arrow is the magnitude, E sub s is the magnitude of the phasor. The projection of the vector along the x-axis is the real part A. The projection along the y-axis is the imaginary part B. And the angle that the blue arrow makes with respect to the x-axis is the angle that appears here, theta. Okay. You can also write it in terms of magnitude and angle form like this, the magnitude at an angle of theta in radians or degrees, either way. Pythagorean theorem tells us that the magnitude is the square root of the sum of the squares of the real and imaginary parts, and also some simple geometry tells us that the angle is the inverse tangent of the imaginary part divided by the real part. Okay. So that's phasors in 2 minutes. Again, if you need more of a refresher on that, if it's been a little while, I highly recommend going back and looking at how we analyzed AC circuits in the frequency domain, because the spirit of the analysis is absolutely identical to what we're about to do here for Maxwell's equations. Okay, well, once we know what a phasor is, we can go ahead and substitute phasors into Faraday's law. Okay, so eventually we'll do this for all the Maxwell's equations, but just starting with Faraday's law. So where there used to be E of R and T, now we're going to put this expression, which is basically the phasor representation of the electric field, and this is the phasor representation of the magnetic flux density B. Okay. Well, what else can we do with that expression? The phasor term, E sub s of R, is the only term that is a function of space. So the curl can be brought inside the curly brackets for the real part like so, because it only acts on the phasor because it's the only part that is a function of space. Okay, so that's what I've done on the left-hand side between equations 18 and 19 here. On the right-hand side, similarly, e to the j omega t is the only term that actually depends on time. So the partial with respect to time comes inside these brackets and acts here only on e to the j omega t. All right. Okay. Now the time derivative of e to the j omega t is simply j omega times e to the j omega t. This should look familiar again from AC circuits. And we can equate both the real and imaginary sides and therefore drop the real part here, drop the restriction to just taking the real part. And also noting when we do that, that e to the j omega t is going to cancel out from both sides of the equation, and we're going to arrive right here at equation 21. This is the frequency domain version of Ampere's law, or excuse me, of Faraday's law. So this is the frequency domain Faraday's law. Okay. If we play the same game with all four of Maxwell's equations, in other words, if we substitute phasors into all four of Maxwell's equations, we end up with the time-harmonic Maxwell's equations right here. These are the time-harmonic Maxwell's equations. So this is the time-harmonic Faraday's law. Curl of the electric field is equal to minus j omega times the phasor representation of the magnetic flux density. The curl of the magnetic field is equal to J plus j omega d. This is Gauss's law right here. Divergence of D is equal to the phasor representation of the charge density, rho sub Vs. And right here, Gauss's law for magnetic fields, the divergence of B is equal to 0. Okay. So again, it is often easier to solve Maxwell's equations in the frequency domain subject to the appropriate boundary conditions. All right. So just like for AC phasor analysis for circuits, what we're going to do is, if we're only interested in the steady state response or the time harmonic response, we'll pass to frequency domain, solve these four equations in frequency domain subject to appropriate spatial boundary conditions. And then once we have expressions for the electric field and the magnetic field, we will pass back to time domain by using this sort of an equation, essentially taking an inverse phasor transform to go back to time domain. Okay. Thank you very much for your attention, and I will see you in the next lecture.